Hello friends, welcome to my lecture on bilinear transformations. In many applications involving boundary value problems which are associated with Laplace equation, we need to find a conformal mapping which maps a disk onto the half plane v greater than 0, where the circular boundary of the disk is mapped onto the boundary of the half plane. V equal to 0 means the real axis of the w plane. An important class of conformal mappings that maps circles to lines and vice versa are the Mobius transformations studied by Auguste Ferdinand Mobius during the period 1790 to 1860. These mappings are also called the linear fractional transformations because they are defined as the quotient of two linear expressions. Now, let us see how we define a Mobius transformation. So, let us say A, B, C, D be four complex constants, where the restriction on the complex constants is that A into D minus B into C is not equal to 0. Then the complex function defined by W equal to Sz equal to Az plus B over Cz plus D is called a Mobius transformation. Now, this transformation can also be expressed as Czw plus dw minus Az minus B equal to 0. When you look at this equation, you notice that this equation is linear both in Z as well as in W. So, this transformation is also called as a bilinear transformation. Now, one more thing we can notice from here, from this equation, Czw plus dw minus Az minus B equal to 0, that is to say Z into, if you collect the coefficient of Z here, Z is multiplied by, if you collect the coefficient here, Z times Cw minus A, Cw minus A is equal to minus dw plus B. We can write this equation as Z times Cw minus A equal to minus dw plus B. Therefore, if W is not equal to A by C, we may write it as Z equal to minus dw plus B divided by Cw minus A. So, if W is not equal to A by C, okay, then we can write the inverse transformation, that is Z equal to S inverse W, which is given by minus dw plus B over Cw minus A. Now, here if you notice that if you take the coefficients of minus D and minus A minus B into C, you see here minus D into minus A minus B into C, this is equal to AD minus BC, okay, and AD minus BC we have assumed to be non-zero, okay. So, Z equal to minus dw plus B over Cw minus A is also a bilinear transformation, okay. You can see how it is a bilinear transformation, because here we said that W equal to Az plus B over Cz plus D, where AD, okay, A into D minus B into C is not equal to 0. Here also we notice that minus D into minus A minus B into C is non-zero. So, it also defines a bilinear transformation, and thus we can say that the inverse of a bilinear transformation is also a bilinear transformation. Now, you can see that if C is equal to 0, then the transformation given by 1, okay, this is the transformation given by 1. If C is equal to 0, W will be equal to Az plus B divided by D. Now, if C is equal to 0, okay, then neither A nor D can be 0, okay. Here you notice that if C is equal to 0, then W is equal to Az plus B divided by D, okay. Since AD minus BC is non-zero, so if C is equal to 0, then neither A nor D can be 0. Okay. So, if C is equal to 0, then neither A nor D can be 0, and therefore, W is equal to Az plus B divided by D is a linear transformation. So, it is a linear mapping, okay, and a linear mapping thus we can say is a special case of a bilinear transformation. Now, furthermore, let us notice that if C is not equal to 0, then we can write Sz equal to this form, as we have Sz equal to Az plus B divided by Cz plus D. Okay. So, if C is not equal to 0, then Sz can also be expressed in this form, A by C plus Bc minus Ad divided by C into 1 over Cz plus D. Now, here you can also see that if Ad minus Bc is equal to 0, okay, if Ad minus Bc equal to 0, then you see that Sz equal to A by C, Sz becomes a constant. Okay. So, we need to put the condition on A, B, C, D that Ad minus Bc must be non-zero. This can also be seen otherwise. We have Sz equal to Az plus B. If you find S prime Z will be equal to a derivative of the numerator, that is A multiplied by Cz plus D minus a derivative of the denominator, that is C multiplied by Az plus B over Cz plus D whole square. Okay. So, this is equal to ACz will cancel, we get Ad minus Bc divided by Cz plus D whole square. So, if Ad minus Bc is equal to 0, then S prime Z equal to 0 for all Z, and so it means that Sz is a constant. Okay. So, to avoid Sz being a constant, we put the condition on A, B, C, D that Ad minus Bc is non-zero. So, if your C is not 0, we can put Sz in this form. Now, from here we notice that if you take A equal to Bc minus Ad by C, this A, you define Bc minus Ad by C equal to A, okay, and B equal to A by C. This A by C we define as B. Then Sz is a composite mapping. It is composition of F, G and H, F, O, G, O, H, Z, where Fz equal to Az plus B, Hz equal to Cz plus D and Gz equal to 1 by Z, which is known as a reciprocal function. The domain of C is the set of all complex numbers C minus d by C. Okay. D by C is not there because it makes Sz to be infinity. So, Sz the bilinear transformation is a composition of two linear functions, this one and one reciprocal function. Now, as I said earlier, S prime Z is equal to Ad minus Bc divided by Cz plus D whole square. Okay. So, this is not 0 because Ad minus Bc is not 0, okay, and since the derivative of Sz is non-zero, okay, over all points Z in the domain of S, therefore, the bilinear transformation defined by Sz is a conformal mapping. Now, further note that if C is not equal to 0, then Sz can be written as Az plus B over Cz plus D equal to A by C into Z plus B by A divided by Z plus D by C. Now, let us denote A by C into Z plus B by A by the function phi Z. Then phi Z is A by C into Z plus B by A, it is a linear function. Okay. So, it is an analytic function, and moreover that we notice that phi minus d by c, if you put minus d by c for Z in phi, then phi minus d by c is equal to A by C into minus d by c plus B by A, which is equal to A by C into minus Ad plus Bc. Okay. So, we are assuming that Ad minus Bc is non-zero, therefore, phi Z is a linear function and phi minus d by c, phi minus d by c is not equal to 0. Okay. So, phi Z is an analytic function and phi minus d by c is not equal to 0 because of the fact that Ad minus Bc is non-zero. Thus, we can say that the bilinear transformation S z equal to phi z over z plus c has a simple pole at z equal to minus d by c. Now, if c is not equal to 0, that is S is not a linear function. We have seen that when c becomes 0, a and d are not 0. So, S is equal to a by d into z plus b by d, okay, and S then becomes a linear function. So, if c is not equal to 0, that is we are assuming that S is not a linear function. It can be viewed as a mapping of the extended complex plane if we consider the limit of S as z tends to the pole and as z tends to infinity. So, when z tends to minus d by c, what we noticed was you see it is limit z tends to minus d by c a z plus b divided by c z plus d. So, we can write a times z plus b by a divided by c times z plus d by c. Now, when z tends to minus d by c, the denominator goes to 0, therefore, S z goes to infinity, and here when z goes to infinity, in order to show that limit of a z plus b over c z plus d as z goes to infinity, we write it as limit z tends to 0, replace z by 1 by z. So, a by z plus b divided by c by z plus d, or we write it as limit z tends to 0, a plus b into z divided by c plus d into z. When z tends to 0, it goes to a by c. So, to determine the limit as z tends to infinity, we replace z by 1 by z in S z and then take the limit as z tends to 0. So, limit z tends to infinity is a by c and limit z tends to minus d by c. Limit becomes infinity when z tends to minus d by c. So, this way we can say that the function S maps the extended complex z plane to extended w complex w plane. So, if c is not equal to 0, we then regard S as a 1-to-1 mapping of the extended complex plane defined by S z equal to a z plus b over c z plus d. If z is not equal to d by c, z is not equal to infinity, S z equal to infinity if z equal to minus d by c, and S z equal to a by c if z is equal to infinity on to itself. Okay. So, S z maps extended complex z plane into extended complex w plane when c is not equal to 0 and it is given by this. When c is equal to 0, we have S z equal to a z plus b divided by d. Okay. So, a by d into z plus b, then S infinity is equal to infinity. Infinities of the two complex planes z and w correspond to each other. Okay. So, S z maps extended complex z plane into extended complex w plane. Now, in particular, if a equal to d equal to 0, okay, if a equal to d equal to 0, b equal to c is not equal to 0, let us see w equal to a z plus b divided by c z plus d. Okay. Here if you notice that if you take a equal to d equal to 0, so this becomes, so if in particular if a equal to d equal to 0, we get b divided by c z, okay, b and c are equal, so this is 1 by z. Okay. So, when a and b d are 0 and b is equal to c not equal to 0, then we get w equal to 1 by z defined on the extended complex z plane. Now, let us show that the class of bilinear transformation carries the class of circles and straight lines onto itself. First, we show the circle preserving property. We know that under the reciprocal mapping w equal to 1 by z, the image of a circle centered at the pole z equal to 0 of 1 by z is a circle, okay, and the image of a circle with center on the x or y axis and containing the pole z equal to 0 is a vertical or horizontal line. and so we are going to see that this property is also possessed by bilinear transformations. Let C be a circle in the z plane and S be the bilinear transformation given by the equation 1, that is Sz equal to Az plus B divided by Cz plus D. Then the mapping of the circle C under S is either a circle or a line in the extended W plane. The image is a line if and only if C is not equal to 0 and the pole Z equal to minus d by C of the bilinear transformation is on the circle C. So, let us first look at the case when C is equal to 0. When C is equal to 0, then we get Sz equal to A z plus B divided by D. Okay. So, A by D into Z plus B by D. We know that when C becomes 0, A and D cannot be 0. So, Sz is a linear function. Okay. And under a linear function we know that only the shape only the size of the figure may be distorted, the basic shape of the figure does not change. So, circles will be mapped into onto circles under this linear map. Now, let us show that the theorem also holds for the case when C is not equal to 0. For the case C equal to 0, we have already resolved that due to the function Sz being a linear function, circles are mapped into circles. So, let us consider C not equal to 0. When C is not equal to 0, then we know that since Sz can be written as FOGOH Z, the composition of F, G and H, where G and H F and G are linear functions, Fz equal to Az plus B, Hz equal to Cz plus D, and are linear functions, and Gz is 1 by Z, which is the reciprocal function. So, since H is a linear function, okay, first of all let us see when you see the effect of S on Z, okay, you have to see the effect of H on Z, because Sz is composition of F, G and H. So, first we see the effect of H mapping on the complex number Z. So, what we see is that since H is a linear function, the image C dash of the circle C under H is a circle. Okay. Now, there arise two cases. Case 1, let us assume that the origin W equal to 0, C origin W equal to 0 is on the circle C dash. So, let us say this is your Z plane and this is your W plane. We have a circle here C, okay, in Z plane, okay, and Hz is this is W is equal to Hz, let us say, okay. Hz we know is Az plus B, okay, and we have seen that under a linear function circles are mapped into circles. So, the circle C maps into a circle C dash. Now, circle C dash may pass through the origin W equal to 0, it may not pass through the origin W equal to 0. So, let us first consider the case where C dash passes through the origin, okay, this is your C dash, okay, circle C dash. So, first let us consider that the origin W equal to 0 lies on the circle C dash. This will happen if and only if the pole Z equal to minus d by C is on the circle C. You can see here W equal to 0, W equal to 0 implies Az plus B equal to Hz was equal to Cz plus D, Hz was equal to Cz plus D. So, when W is equal to 0, Cz plus D equal to 0, which will give you Z equal to minus d by C, and we know that Z equal to minus d by C is the pole of the bilinear transformation. So, this means that pole Z equal to minus d by C is on the circle C. Okay, because W plane is in the W plane, C dash is the image of C, and the point W equal to 0, okay, corresponds to the point Z equal to minus d by C. So, Z equal to minus d by C lies on the circle C. Okay. Now, if W equal to 0 is on C dash, okay, then the image of C dash under Gz equal to 1 by Z is a straight line. Okay. So, this we can see very easily. The circles are straight lines in the W plane is given by this equation. Let us say some constant, real constant A times mod of W square plus 2 times real part of B into W plus C equal to 0. Okay. The circles are straight lines in the straight lines are circles. In the W plane are given by this equation in complex, are given by A mod of W square plus 2 times real part of B W plus C, where A and C are real constants, A C belong to R and B is a complex constant, B belongs to C. Okay. So, if W equal to 0 lies on this circle, W equal to 0 lies on C dash, then what do we get here? Putting W equal to 0 we get C equal to 0. Okay. So, C equal to 0 means now the equation reduces to A times mod of W square plus 2 times real part of B W equal to 0. Okay. Now, let us see it the image of this circle, okay, image of this circle under the transformation G Z equal to 1 by Z. Okay. So, let me say that Xi is equal to G W equal to 1 by W. Okay. So, let us say from W plane we are now going to Xi plane. Okay. So, Xi is equal to 1 by W. So, we put W as 1 by Xi here. So, A times 1 over mod of Xi square plus 2 times real part of B over Xi equal to 0, or we can say that this is A times 1 over mod of Xi square plus 2 times real part of B times Xi conjugate divided by Xi conjugate is mod of Xi square equal to 0. Now, we can multiply this equation by mod of Xi square. Mod of Xi square is a real quantity, so it will come out of the real part. So, we can get A plus 2 times real part of B Xi conjugate equal to 0. Okay. And A is a real constant, we know 2 times real part of B Xi conjugate equal to 0. If Xi conjugate Xi is equal to, suppose we write Xi equal to say eta plus I zeta, let us say, okay, zeta as Xi as eta plus Xi eta plus I times zeta, then Xi conjugate will be eta minus I zeta. Okay. And B if you take as alpha plus I beta, then what do we get? Let me clarify this. This is A plus twice B times Xi conjugate equal to 0. So, A plus 2 times B is a complex constant, I can write as alpha plus I beta. Xi conjugate is we have taken Xi as eta minus Xi conjugate is eta minus I zeta. So, eta minus I zeta equal to 0. Okay. And this is real part, real part. So, A plus 2 times, now we can take real part here. So, real part is alpha eta and then minus I square beta zeta. So, this means that plus beta zeta equal to 0. So, what do we get? 2 alpha eta plus 2 beta zeta plus A equal to 0. Okay. So, if Xi is equal to eta minus eta plus I zeta, okay, that means in the Xi plane, this is your eta, this is your zeta axis. Okay. In the Xi plane, the equation comes out to be 2 alpha eta plus 2 beta zeta plus A, okay, equal to 0, where alpha, beta, A and are real numbers. So, this represents a straight line. And therefore, we can say that the image of C dash under G z equal to 1 by z is a straight line, says we denote it by L. Okay. Now, since f is a linear function, okay, now we have seen the effect of H mapping and then G mapping. Now, we have to see the finally effect of F mapping. So, now since f is a linear function, the image of this straight line L under f is also a line. Hence, if the pole z equal to minus dy c lies on the circle C, then the image of C under S is a line. Now, let us take the case 2. Let us assume that w equal to 0 is not there on C dash. Okay. Then, under the mapping H, okay, H z is equal to, let us recall, H z equal to C z plus D. Okay. And circle C is mapping into circle C dash under the mapping H z. Okay. So, if z w is equal to 0 is not on C dash, okay, then w equal to 0 corresponds to z equal to minus dy c. Okay. So, if w equal to 0 is not on C dash, then z equal to minus dy c is also not there on the circle C, and z equal to minus dy c, we know that it is the pole of the bilinear transformation. So, if w equal to 0 is not on C dash, then the pole z equal to minus dy c is not on the circle C. Now, let us say that the equation of the circle C dash in the w plane is this w we have defined as w equal to h z here. Okay. So, in the w plane, let us say the equation of C dash be given by mod of w minus w naught equal to rho. Now, since w equal to 0 is not on C dash, remember w equal to 0 is not on C dash. So, this means that mod of w naught is not equal to rho. Okay. W equal to 0, w equal to 0 if you put here, then we get mod of w naught equal to rho. So, if w equal to 0 is not on C dash, then mod of w naught is not equal to rho. So, that implies from here. Now, let us set xi equal to gw. So, from w plane now we are going to xi plane. Okay. So, this is your w plane. In the w plane we have the circle C dash, okay, which does not pass through w equal to 0, and from here we are going to xi plane. Okay. Xi plane. Okay. Xi equal to, you can say eta zeta. Okay. So, here we are setting gw equal to xi and gw equal to 1 by w. So, what do we get? Xi naught is equal to, let us say, gw naught. Okay. The point w naught, which is the center of the circle C dash, w naught is the center of the circle C dash. Suppose it is mapped into xi naught, then xi naught is equal to 1 by w naught. Okay. Now, take any point w on C dash, take any point w on C dash, then let us look at the value of mod of xi minus xi naught. Mod of xi minus xi naught is equal to mod of 1 by w minus 1 by w naught, which is mod of w minus w naught over w naught. Okay. Now, this is equal to rho times mod of xi naught into mod of xi, you see, because mod of w minus w naught is rho, mod of w minus w naught is equal to rho, 1 by w, mod of 1 by w is mod of xi, and mod of 1 by w naught is mod of xi naught. So, this is equal to rho times mod of xi naught into mod of xi. Now, let us look at the equation mod of xi minus a minus lambda times mod of xi minus b. Now, it is known that mod of xi minus a equal to lambda times mod of xi minus b represents a line if lambda equal to 1, and it represents a circle if lambda is greater than 0 and not equal to 1. This is very simple, we can easily prove this. So, let us suppose we have mod of xi minus a equal to lambda times mod of xi minus b. Okay. Xi is equal to eta plus xi eta plus I zeta, and a we can take as say alpha 1 plus I beta 1, and b we can take as alpha 2 plus I beta 2. Then mod of xi minus a equal to lambda times mod of xi minus b, let us square both sides. So, we get mod of xi minus a square equal to eta minus alpha 1 whole square plus zeta minus beta 1 whole square equal to lambda square times eta minus alpha 2 whole square plus zeta minus beta 2 whole square. Now, if lambda is equal to 1, okay, if lambda equal to 1, then what will happen? This will be, you can open this, this is eta square minus 2 alpha 1 eta plus alpha 1 square plus zeta square minus 2 beta 1 zeta plus beta 1 square equal to eta square minus 2 alpha 2 eta plus alpha 2 square plus zeta square minus 2 beta 2 zeta plus beta 2 square. Okay. So, when lambda is equal to 1, you can see the square terms eta square zeta square cancel, and what we have? We have the equation of a straight line. You can collect the coefficients of alpha, eta and zeta. Okay. So, we get 2 times alpha 2 minus alpha 1 into eta, okay, and then we get 2 times beta 2 minus beta 1 into zeta, and then we get alpha 1 plus beta 1 square minus alpha 2 square minus beta 2 square equal to 0, which is the equation of a straight line in the eta zeta plane. Okay. So, if lambda is equal to 1, mod of xi minus a equal to mod of xi minus b represents a straight line. Okay. But if lambda is not equal to 1, what will happen? Then eta square zeta square term will not cancel. So, if lambda is not equal to 1, okay, then this equation implies that we will have eta square times 1 minus lambda square, okay, eta square times 1 minus lambda square, then we have minus 2 alpha 1, okay, and then we will have zeta square here we will have lambda square zeta square. So, we will have lambda square 1 minus lambda square, this is zeta square, zeta alpha eta square into 1 minus lambda square plus zeta square into 1 minus lambda square. We have minus 2 alpha 1 eta, and here we will get minus 2 alpha 2 lambda square eta. Okay. So, we will get that as plus 2 alpha 2 eta lambda square. Okay. And then we can have here similarly minus 2 beta 1 zeta here from here minus 2 beta 1 zeta, and here we will get minus plus 2 beta 2 zeta into lambda square. Okay. And then we will have alpha 1 square beta 1 square lambda square alpha 2 square with the negative sign and minus lambda square beta 2 square. Now, you can look at this equation. Okay. In this equation you see that the coefficient of eta square and zeta square are same, 1 minus lambda square, 1 minus lambda square, and lambda is not equal to 1. So, the coefficients are not 0, and therefore, this equation represents a circle. Okay. So, mod of xi minus a equal to lambda times mod of xi minus b represents a straight line when lambda equal to 1, and it represents a circle when lambda is greater than 0, but not equal to 1. Okay. So, we see that this equation represents a line if lambda equal to 1 and a circle if lambda is greater than 0, but not equal to 1. Now, we find that the set of points given by this equation mod of xi minus xi naught equal to rho times mod of xi naught into mod of xi naught into mod of xi is a circle. Why? Because w naught mod of w naught is not equal to rho, we have seen earlier. Okay. W equal to 0 does not lie on the circle C dash. So, mod of w is not equal to mod of w naught is not equal to rho. Okay. And so, lambda is equal to rho xi naught. Okay. Let us put this lambda rho xi naught as lambda. So, lambda equal to rho mod of xi naught equal to rho times mod of xi naught is 1 over w naught. Okay. So, rho into 1 over w naught, this is not equal to 1. Okay. because of this. So, rho into 1 over mod of W naught is not equal to 1, that means lambda is not equal to 1. So, this is not equal to 1. So, mod of xi minus xi naught equal to some lambda times mod of xi. Now, this can be compared with this equation. You can see mod of xi minus xi naught equal to, this is lambda mod of xi minus 0. Okay. So, taking xi naught equal to a, okay, lambda equal to rho mod of xi naught and b equal to 0. We can compare this equation with this equation. Okay. So, what do you notice that lambda is not equal to 1 here, therefore, this equation represents a circle. Okay. So, the set of points given by this equation is a circle. So, this means that the circle C dash, when does not pass through the origin, maps into a circle in the xi plane. Now, finally, since f is a linear function, the image of this circle in the xi plane under f is again a circle, and so we conclude that the image of C under the bilinear transformation S is a circle. So, this proves the theorem. Similarly, we have the other theorem which says that again if Sz is a bilinear transformation, then the image of a line L. Now, we will take the case of a line. Earlier in the theorem 1 we took the case of a circle, in the z plane we took a circle and we saw its image under S, whether it is a line or a circle. Now, here we will take the line in the z plane and we will see what happens under the bilinear transformation S. What is the image of the line L under S. Okay. So, if S has Sz equal to Az plus B over Cz plus D, then the image of a line L under S is either a line or a circle. Now, the image is a circle if and only if C is not equal to 0 and the pole Z equal to minus dy C is not on the line L. Now, let us see how it happens. So, if C is equal to 0, then as we noticed earlier, Sz equal to A by D into Z plus B by D, okay, which is a linear function. So, linear functions preserves the shape of the figure. So, if it is a straight line, it will remain a straight line under the mapping Sz. Okay. So, the straight line L will be mapped into a straight line. Now, let us assume then that the C is not equal to 0. When C is not equal to 0, we recall that Sz can be expressed as the composition of f, g and h, f, o, g, o, h, where f, z and h, z are linear functions, okay, and g, z equal to 1 by z is the reciprocal function. Now, since h is a linear function, h, z equal to c, z plus d, the image L dash of the line L under h is a straight line. Now, again there arise two cases like in theorem 1. Okay. So, first case is that the line passes through the origin, okay, the straight line L dash in the W plane. Okay. This is your Z plane. We have taken any straight line L, okay, in the Z plane. Okay. Now, it is mapped into straight line L dash in the W plane under the mapping H z, W equal to H z and H z equal to C z plus, no, H z not C z plus H, okay, H z equal to C z plus D, right. Okay. So, the line L dash may or may not pass through the origin W equal to 0. So, let us consider the case when it passes through the origin. Okay. This is your L dash. So, assume that the origin W equal to 0 is on the straight line L dash. This means that now W equal to 0 lies here. Okay. So, this means that my W equal to 0 will give you C z plus D equal to 0. This means that Z equal to minus dy C. Okay. So, Z equal to minus dy C, okay, will lie on L, okay, and we know that Z equal to minus dy C is the pole of the bilinear transformation. So, if W equal to 0 is on the straight line L dash, then Z equal to minus dy C lies on the straight line L. If W equal to 0 is on L dash, then the image of L dash under g z equal to 1 by z is a straight line. Now, let us see how we get this. So, as we have seen earlier, the totality of straight lines are circles, the circles and are straight lines, and straight lines are given by, in the W plane they are given by this equation. W plane are given by A times mod of W square plus 2 times B W, okay, plus C equal to 0, where A, C belong to R and B belongs to C. Okay. Now, here we have assumed that W equal to 0 lies on L dash. Okay. So, W equal to 0, let us put in this, we are going to see the under the mapping G z equal to 1 by z what happens to the image of L dash. Okay. So, W equal to 0 lies on C dash, okay, this C dash. Okay. So, then this C is equal to 0. Okay. This means that we have A times mod of W square plus 2 times B into real part, this should be real part here, B W equal to 0. Okay. So, if W equal to 0 lies on L dash, then the image of now we are taking it as a line, okay, L dash. So, L dash, if it is a line, then A must be 0. Okay. So, it should not be, this term should not be there. Okay. So, we have this equation, this is the equation of a line, okay, equation of line, the straight lines in the W plane. The straight lines in the W plane are given by this equation, okay, because if A is non-zero, then that will represent a circle. So, 2 times real part of B W plus C equal to 0. Now, C is equal to 0. So, what do we get? We will get this as twice real part of B W equal to 0. Okay. So, now let us consider G W equal to xi and G W equal to 1 by W. So, from W plane we are now going to, from this plane we are now going to xi plane. So, 2 times real part of B, let us again take as alpha plus I beta, and then we will have W is equal to 1 by xi. So, this is equal to 0. Okay. Now, what do we do? Let us multiply by xi conjugate. So, this will be, let me write here. Okay. So, twice real part of alpha plus I beta into xi conjugate divided by xi conjugate equal to 0. Okay. So, this will be xi conjugate is mod of xi square. Okay. So, it will come out of the real part. So, 2 times mod of xi square and we have real part of alpha plus I beta into eta minus I zeta. This is your xi plane, eta zeta. Okay. So, now you can see the real part, if you take, it will give you 2 times mod of xi square times will have alpha eta, okay, minus plus beta zeta. Okay, this is real part, alpha eta plus beta zeta equal to 0. So, alpha eta plus beta zeta equal to 0 means, okay, the line passes through the origin in the zeta plane. Okay. Alpha eta plus beta zeta equal to 0 means the line passes through the origin in the so straight line, again we get a straight line which passes through the origin. Okay. So, when you take the straight line in the z plane under the mapping h z, it maps into the straight line L dash. L dash, if it passes through the origin, then its image under g z equal to 1 by z is again a straight line which passes through the origin. Okay. So, this is what we get. Now, furthermore, now we have to see the effect of f. So, further, if f is, since f is a linear function, the image of the line in the xi plane under f is again a line. So, if the pole z equal to minus d by c lies on the line L, then the image of L under S is a line. Now, let us assume that W equal to 0 does not lie on L dash. If W equal to 0 does not lie on L dash, then W equal to h z is equal to C z plus d will imply that W is equal to 0 implies and implied by Z equal to minus d by c. So, when W equal to 0 does not lie on L dash, then Z equal to minus d by c also does not lie on the line L. Now, L dash let us say be given by the line L dash in the W plane, suppose it is given by Bu plus Cv plus d equal to 0. This is the equation of the straight line L dash in the W plane. You can see here we have taken the constant d because this line does not pass through the origin. Okay. So, let us see what happens to this under the mapping Gz equal to 1 by Z. So, let us set xi equal to Gw equal to 1 by W, then Bu plus Cb plus d equal to 0 gives you we have xi equal to 1 by W. So, W equal to 1 by xi. Okay. So, u plus Ib I can express as xi conjugate divided by xi conjugate. So, xi conjugate divided by mod of xi square. So, u is equal to, if xi is eta plus I zeta, then it is eta minus I zeta. Eta plus I zeta. Okay. So, then u is equal to eta divided by mod of xi square, which is real part of xi divided by mod of xi square, and b is equal to minus imaginary part of xi divided by mod of xi square. So, let us put these values of u and b in this equation. So, we get b times real part of xi divided by mod of xi square. I have multiplied the equation by mod of xi square, and then minus c times imaginary part of xi plus d times mod of xi square equal to 0. Now, since W equal to 0 does not lie on L dash, okay, so what will happen? W equal to 0, this is not does not lie on L dash. Okay, so, under the mapping xi equal to 1 by W, what happens? D cannot be 0 because D is equal to 0 means u and b are zeros. Okay. D equal to 0 means see, when W equal to 0 lies on L dash, u and b both will be 0, u and b both will be 0. So, D will be 0. Okay. So, W equal to 0 does not lie on L dash means D cannot be 0, and hence what do we have? This coefficient of mod of xi square. Okay. This D is non-zero, and therefore, b real part of xi minus c imaginary part of xi plus d times mod of xi square. Mod of xi square is eta square plus zeta square. So, eta square plus zeta square term will be there in this equation in xi eta. So, this equation represents a circle. So, the image of L dash under G is a circle. Now, since f is a linear function, the image of this circle under f is again a circle. So, this is the proof of theorem 2. Now, let us see how we find the image of the unit circle mod of z equal to 1 under the bilinear transformation as z equal to z plus 2 over z minus 1. So, let us see, this is our circle mod of z equal to 1. Okay. Now, we see that z equal to 1 is the pole of Sz. Okay, as z equal to 1 is the pole of the bilinear transformation Z, and z equal to 1 lies on mod z equal to 1. Z equal to 1 lies on mod z equal to 1. So, let us go to theorem 1. So, it says that let C be a circle in the z plane. We have unit circle in the z plane. S is the bilinear transformation given by 1. Then the image of C under S is either a circle or a line in the extended W plane. The image is a line if and only if C is not equal to 0 and the pole is on the circle C. Okay. We have seen that the pole z equal to 1 lies on the circle C, therefore, image must be a line. So, in this example, first conclusion from theorem 1 is that, okay, since z equal to 1 lies on mod of z equal to 1, okay, hence the image of mod of z equal to 1 under S must be a line. Now, we need 2 points to draw the line. Okay. So, let us take 2 points on the circle here and let us find their image, then we will be able to draw this line. So, let us take one point as say -1, okay. One point as -1 on this circle, another point let us take as I. Okay. Then S -1, we can see S -1 is 2 minus 1 divided by -2. Okay. So, this is -half. Okay. And S I, if you find S I is I plus 2 divided by I minus 1. So, I can write it as I plus 2 into I plus 1 divided by I square minus 1, and this gives you how much? This is equal to I square. So, minus 1 plus 2 I plus I plus 2 divided by minus 2. So, what we get here 3 I by minus 2, 3 I okay, 3 I plus 1 divided by minus 2. So, this is equal to minus half minus 3 by 2 I. Okay. So, we have got the image of 2 points on the circle in the z plane. So, the image of the 2 points on the circle is this one is minus half, the other is minus half minus 3 by 2. So, let us draw in the W plane, okay, this figure. So, see minus S minus 1 goes to minus half, this is minus half here. Okay. So, this is U B, let us say minus half here, and minus half minus 3 by 2 is here. Okay. So, minus half minus 3 by 2 I. So, this is the line, that is U equal to minus half. The line is U equal to minus half, that is the line parallel to the imaginary axis in the W plane. Now, let us take the image of the interior mod z less than 1. So, we know that S z equal to mod of z plus 2 over z minus 1 is a rational function of z, and therefore, it is a continuous function of z at each point of its domain. Okay. So, let us take the point z equal to 0. Okay. Z equal to 0, it lies in mod of z less than 1, and under the mapping S z, let us see where that is, does it go. Okay. So, S0 comes out to be minus 2. Okay. So, the interior, there is a point we have taken as a test point in the interior of mod z, interior of the circle at origin we have taken, and it goes to minus 2, and minus 2 lies here. Okay. That is in the left side of the line U equal to minus half. Therefore, the region inside the circle mod z equal to 1 maps to the lower left half of the line U equal to minus half. Okay. So, mod z less than 1 is mapped into U less than minus half in this region. Okay. This is the example 1. Now, let us say the example 2, find the image of the circle mod z equal to 2 under the same bilinear transformation we are taking. Okay. Now, here let us notice that the pole z equal to 1 does not lie on mod z equal to 2. So, what does the theorem say? Theorem says that let C be a circle in the z plane. Now, we have the circle mod z equal to 2, S is the bilinear transformation, then the image of C under S is either circle or a line in the extended W plane. The image is a line if and only if C is non-zero, and the pole minus at minus d by C is on the circle. So, pole is not on the circle, therefore, the line is not the image of the circle is the circle. So, we notice from the theorem that the image of mod of z equal to 2 is a circle. Okay. So, from theorem 1, the image of mod z equal to 2 is a circle. Okay. Now, let us draw the circle mod z equal to 2. So, this is mod z equal to 2. We can see that it is symmetric about the real axis, okay, also about the imaginary axis. So, mod z equal to 2 is symmetric about x axis. This means that if z is a point on the circle, okay, then z conjugate is also a point on the circle. Okay. If z is a point on the circle mod z equal to 2, then z conjugate is also a point on the circle mod z equal to 2. Now, let us say that let w be equal to f z. Okay. So, suppose z goes to w in the w plane, okay. Then let us see where does this z conjugate go. Okay. So, S z conjugate, let us see what is S z conjugate. S z conjugate is z conjugate plus 2 divided by z conjugate minus 1, okay. And this I can write as z plus 2 conjugate divided by z minus 1 conjugate, and this can also be written as z plus 2 divided by z minus 1 whole conjugate. Okay. So, and this is what? This is conjugate of S z. So, S z conjugate is equal to conjugate of S z. Now, what does it mean? Okay. S z equal to W. Okay. So, what do you notice? W conjugate is equal to S z conjugate is equal to S of Z conjugate. So, if Z goes to W, then Z conjugate goes to W conjugate. Okay. This means that if W lies on the circle, then W conjugate also lies on the circle. So, the image of mod of Z equal to 2 in the W plane must be symmetric about the real axis. So, the circle in the W plane is symmetric about the real axis. Okay. Now, let us take 2 points on this circle mod z equal to 2. Let us take z equal to 2 and z equal to minus 2 and see their images under S z. Okay. So, S 2 you can see S 2 equal to 4, okay, and S minus 2 equal to 0. Okay. This means that the circle in the W plane is symmetric about the real axis, okay, and the point 2 and minus 2 go to 0 and 4, which also lie on the real axis. This means that 0 and 4, because of the symmetry, must be the ends of a diameter of that circle. Okay. So, we can say that circle is like this, 0 and 4. 0 and 4. Okay. So, this is 0, this is 4. Okay. So, that means 2 0 must be the center of the circle and radius must be 2. Okay. So, we have the equation of the circle as mod of W minus 2 equal to 2. Okay. Now, let us ask whether the what is the image of the interior of this circle, okay, mod z equal to 2. So, suppose you take again z equal to 0 here, z equal to 0 maps to S 0 equal to minus 2, okay, S 0 equal to minus 2, and minus 2 does not lie lies outside this circle, minus 2 is here. Okay. So, this means that interior of the circle is mapped onto the exterior of mod of W minus 2 equal to 2. So, mod z less than or equal to 2 is mapped into the mod of W minus 2 greater than or equal to 2. Okay. So, that is the conclusion which we can draw. So, this is mapped into mod of W minus 2 greater than or equal to 2. Okay. So, with this I will come to the end of this lecture. Thank you very much for your attention.